This is an example of the first order transient game at the mastery level in Circuit Tutor. And in particular, this is going to be a game involving a capacitor. Okay, so we'll click on the hard level. And as I said, this case involves a capacitor, and also we have a dependent source, which means that this is going to be a little bit more complicated approach, particularly when we find the R-Thevenin value. So let's begin, as always, by analyzing the circuit at several successive times, starting out at t equals 0 minus. So it gives us the instructions, as usual, to first reconfigure the circuit, then simplify it appropriately and solve it. So click the button to reconfigure. And in this mode, again, we're not allowed to simplify the circuit, but we basically will alter the switches. So for t equals 0 minus, this switch is opening at t equal to 0. So it's going to be closed or a short circuit at t equals 0 minus. We change that to a short. And then for the capacitor, it already has a sought voltage, and of course if it didn't, we would need to supply one there, because that's the one thing that will not change suddenly as the switch actuates, because again, capacitor voltage cannot change suddenly without causing an infinite current, because I equals c dv dt. Therefore, we can change this, since it's going to be in steady state at 0 minus, since the switch will have been in its position for a long time. That means that this will be basically an open circuit, because again, I equals c dv dt, v will not be changing with t, so that derivative will be 0, and the current is 0, equivalent to an open circuit. So we're going to change that to a set of terminals in order to preserve the sought voltage that we need to find here at this time. Okay, so that's all we need to do for reconfiguring the circuit. And now we can look and see if any simplification is possible in this case, and I don't see really anything that can be done here. Except for one thing, there is a 1 ohm resistor here that we notice is going to be shorted, so we will get rid of that to simplify the analysis. So we'll just select that and delete it. And having done that, basically there's nothing else we can do. We can't do a source transformation here because this has a control variable, and you can never transform a source or passive element that has a sought or control variable on it, because that would lose that variable that we need. And basically there's nothing else that we can do to simplify this, so we're done editing. And now for analysis, it probably makes most sense to do a mesh analysis here, since there's only two interior meshes. So let's select mesh analysis in this case, and it'll give us the usual instructions for that. And so we've automatically selected the outer mesh here as the reference mesh, so we have the halt symbol there. And we'll begin by writing KVL equations for any mesh that does not contain a current source. So we see for mesh 2, there is no current source, so we're allowed to write a mesh equation there. So we'll select mesh 2 with the selector, and then we'll click done there. And we'll just go around clockwise here, adding the voltage drops around that mesh. So the first one will be a current times the resistance, then we have an independent voltage source, and finally we have a resistor that has two interior mesh currents through it, or non-reference mesh currents, and that has to sum to 0. So first we have I1, and then that's going to be times the 1 ohm. And then we have plus 6 volts, since we reached the plus sign first. That is in fact a drop, so that has a plus sign. And finally then we have I2 minus I1 times the 4 ohms will be the last voltage drop going around this way in the direction, of course, of I2. So we check that equation, and looks like I made a mistake there. Oh, I put in the wrong current here, so that should have been I2, because I'm going around, of course, mesh 2. That was just a typo there. So let's try that again, and that is correct. Now we cannot write a KVL equation for mesh 1 because it has a current source, which would make that impossible, and it'll generate an error if I try to do that. So instead, we're going to write a current constraint equation for mesh 1. And so that simply tells us that I1 will be equal to the value of that source, since they go in the same direction. So I1 will have to be equal to 1 amp. And we'll check that. Oh, I somehow got an extra equal sign in there. Okay, try that again. Okay, and now we need a control variable equation for the control variable of the dependent source, which is the Vx quantity. So we'll select a control variable equation. So that is going to be given by, of course, Ohm's law. Since there's one current going through, one non-reference mesh current going through that resistor, we'll choose this type of term here. And then we'll fill that in as Vx. And notice here that because the mesh current goes into the negative side of that voltage, Ohm's law here will have a minus sign. We always have to check the polarity on Ohm's law. So that would be minus I2 times the 1 ohm. And finally, we need the slot variable equation for the capacitor voltage at 0 minus, which is going to be a branch voltage there. It's actually across the capacitor, even though it's not shown. Okay, and it is giving us a warning here, which says that if we need to write a KVL equation and the simplest path does not work, which would be the one here, which we can't use, as you see, because we have a current source there, then it says use a different simple mesh containing the SOT voltage instead, which might be the outer mesh. Circuit Tutor doesn't currently support equations written for other paths, even though they may be valid. Now we're working on adding support for that in the future, but at the moment that's not available yet. So what that means is I will have to take a path, because I cannot, as I said, use this mesh because we don't know the voltage across the current source. Now you could say, well, we could use this path, and that would actually be correct, but as I said, Circuit Tutor, as that warning just told us, is not going to support that. So instead we need to go around the outer mesh through this path. So we're going to do that. So we have VC of 0 minus, and basically we're going to go from this side through the outside of the circuit. So we're going to have I2 times the 1 ohm, and then we have the 6 volt drop, and then we're going to go through the dependent source. So we need this type of term, and that will be it, because remember that there is no voltage drop across the 6 ohm resistor because it's dangling essentially. This is the DC capacitor, or the steady state capacitor here, is an open circuit, and so there's not going to be any voltage drop there, so we do not have a term for the 6 ohm resistor. So here we'll add in the 6 volt drop here, and again I'm going from the plus side to the minus side and adding the voltage drops, which will give me the correct value for VC of 0 minus. And then here we encounter the negative sign first, so that's going to be a minus 6 Vx, because that's actually a voltage rise and going from the plus side to the minus side. So we can check that equation, and that is correct. So now we've written all the equations that we need. And so now it wants us to put this into simplified equations. So we'll do that. The first one is very simple. So I1 equals 1. We just have a coefficient of 1 in front of I1 and a 1 over here. The second equation, we look at the coefficient first of I1. That's going to be -4. And then the coefficient of I2 is going to be 1 plus 4. That's going to be 5. And of course no Vx, but the 6 is going to go over to the other side and become a -6 on the constant. And then the control variable equation, that's equivalent to Vx plus 1 I2. So Vx will have a 1 and I2 will have a 1. And that should be it. So now we just check that, and those are correct. And then we'll just copy that into the matrix equation. We can use the copy button rather than retyping everything. And so that's the matrix equation. And now we need to solve these, although this is actually going to be a pretty easy case. I think if we look at these equations, we don't probably really need to do any formal Gaussian elimination, because this first block basically is independent of the rest. So first of all, we can say, well, we already know I1 is 1 amp, so that one we have immediately. And to find I2, Well, we can basically just kind of look at this equation and imagine substituting I1 equals 1 into that. So we're going to basically have a negative 6 on the right, and then as we put that in as a 1, then we're going to add that and get a negative 2 on the right as we add 4 to that. And then we divide by the coefficient of the I2, which is going to be 5. And so basically that's going to be a negative 5/4, or I'm sorry, negative 2/5, I mean, negative 2/5 or negative 0.4. Okay, so again, very simple algebra because it's just one equation essentially and one unknown after we make simple substitutions there. And we can check that. And finally, we just have to crank the numbers and find the sought variable. So we're going to use this equation. And the I2, again, is the negative 0.4. And that add to 6 would be the 5.6. And then we have to subtract minus 6 Vx. And that's going to be minus 2.4. And so just adding that up gives us 3.2 volts. And so we have found Vc at 0 minus as being 3.2 volts. So that's what we need there. And in this case, the sought variable is a capacitor voltage, which we know cannot change instantaneously with time. So that will make it rather easy to find the value of Vc at 0 plus. It's simply going to be the same as it is at 0 minus. So in this case, all we have to do is to enter that same voltage again. There's really no circuit analysis that's actually necessary in this case because the sought variable is a capacitor voltage. Okay, now we're going to analyze at t equal to infinity when the circuit will again be in steady state, but now with a different switch position. So again, we get the instructions. We have to first reconfigure the circuit, then edit it if necessary or simplify it, and then write the equations. So let's begin by reconfiguring the circuit. And once again, we have to set the switch to have a definite character. And so in this case, at t equals infinity, of course, is long past 0, so this switch is open. So I'm simply going to delete that switch, change it to an open circuit. And again, we can't simplify in this mode, so we just are limiting ourselves to the reactive element and the switch. And now we know that the capacitor will once again be an open circuit because again, I equals C dV dt, and the dV dt must be 0 in steady state as the time derivative of anything is in steady state. So the current will be 0, so that's an open circuit. So I'm going to change that to terminal so that I can preserve my sought variable here. If I delete it, then I won't have a way to label that voltage in Circuit Tutor. So that basically finishes that, and we're done reconfiguring. And of course, if I'd made a mistake anywhere there, I could have just pressed the restore circuit key to start the process over again. Okay, so now let's see if we can simplify something. Well, I see some resistors in series, so there's probably at least a little bit we can do there. So let's just combine the 4 ohm and the 1 ohm in series, and that adds, of course, to 5 ohms. So we'll change this one to a short and check that combination. And then we can look to see if anything else can be done. Again, we cannot do a sought variable transformation there. And really, there's nothing else that can be done there. So that's going to be all we can do. And once again, let's do a mesh analysis. Since we do have the current source as a constraint, that will simplify the mesh analysis down to basically one equation and one unknown, which can't do much better than that. So let's do a mesh analysis. And let's again write a KVL equation for the current in mesh 2. And so we'll select mesh 2 there and select that with the selector there. And so the first voltage drop is going to have a current times the resistance. So it'll be that type. And then we have a voltage drop of an independent source, which needs that type of term. And finally then a resistor shared between two meshes now. So that will be this type of term. And that's equal to 0. So then we'll just fill in the blanks here. So we have I2, make sure I get that right this time, times the 1 ohm. And then again 6 volt drop as we had previously. And then we have I2 minus I1 times the 5 ohms, again for the voltage drop across the 5 ohm resistor, getting back to where we started, and so that should be the result, which it is. We can, again, not write a KVL equation for mesh 1 because of the current source, whose voltage is whatever it needs to be, and since we don't know it, we cannot write that equation. So instead, we do a current constraint equation for mesh 1. So I1 will just have the value of 1 ampere again, as it did at 0 minus. So I1 equals 1 amp. Now notice the circuit is changed, but that part is still the same. Okay, so we'll check that. And then, of course, because we have a dependent source, we do need to write an equation again for its control variable. So write a control variable equation for Vx. And once again, that will just be a current times a resistor. So we'll fill that in as Vx. And once again, I2 is going into the negative side of that, so it has a minus sign in Ohm's law. And then that's going to be I2 times the 1 ohm. Then we need the slot variable equation for Vc of infinity, so that's going to be a branch voltage again. And it does give us, again, that reminder to go around the outside of the circuit if we're unable to use this mesh, which is going to be the same problem we had before. So we have to go around the outside of the circuit, not around this path, even though technically that would be valid to do, but it won't be recognized as correct in Circuit Tutor. So let's avoid that aggravation. Okay, so Vc of infinity is going to be equal to, we need first a voltage drop across a resistor with one non-reference mesh current, then the independent voltage drop, and then going around the outside, the dependent source value for a voltage-controlled voltage source, and finally, well, that's it, because again, no voltage drop here because, once again, this is dangling, being in steady state. So we'll fill that in now, as that's the I2 times the 1 ohm. And remember that this has nothing to do with the polarity of the Vx value because that's just the control voltage. We're not using the control voltage right now. Okay, then we have the 6 volt drop, which is a positive drop there. And then we have minus because this is actually voltage rise. And then that will be the 6 times the Vx. And that should complete that equation. And that is correct. And once again, we're done with our equations. So we'll click no more equations. And it's going to ask us to put those into simplified form here, although to be honest, we probably wouldn't really need to do that in this case, but the program asks us to do it. So we have 1 times I1 is equal to 1. And then we have minus 5I1 in this case. And then the I2 has 1 plus 5 is going to be 6. So its coefficient is 6. And then I'm going to have a negative 6 on the other side for the source value. And then finally we have Vx plus I2 basically equals 0. So that's going to have a 1 there and a 1 there. A 1 and 1 rather than a 10 actually. And that's it. So now we just check that. That is correct. And we can copy that into the matrix equation. And then, again, this is going to be, once again, fairly simple because we can, first of all, know I1 is already 1 amp, as it was previously. And once again, we can solve this equation for I2. The Vx doesn't come into it, so basically we just put the I1 equal to 1 here. And so see that that's going to be a basically a minus 5 here, which is going to, and then I have a negative 6 goes on the other side, and then I add the 5, so that gives us a negative 1 divided by the coefficient of the I2, which is going to be 6. So basically it's negative 1/6, or negative 0.1667. And that's correct. And then we just need to compute from this equation the value of Vc. So I2 times 1, basically that's 1/6 times 1, so that's 1/6 plus 6, so that's 6.166, and then minus 6 Vx. Well, 6 times 1/6 is 1, so that's minus 1, so that's basically 5, well, 5 minus the 6, so that's going to be 4.833. 4 and 5/6 in other words. Okay, so that's done. And now we've computed that. So the last task here is to find our Thevenin seen again from the terminals of the capacitor. So let's do that step. And again, as usual, we have to first reconfigure the circuit with the switch and the reactive element, then perhaps simplify if appropriate. And if we're using a test source, then we have to write equations. And in this case, we know that we are going to need a test source because we have a dependent source here. So we cannot simply use resistive simplification. So let's go into Reconfigure now. And first we have to deal with the switch. So again, because t is greater than 0, we're only interested in the time constant for t greater than 0 because that's what's relevant to our transient. The time constant for t less than 0, that transient died out before we even started analyzing, so we don't care about that. So we're only interested in doing this for t greater than 0, and at that time this switch is open. So I'm going to delete that switch. Now, normally I could put in terminals here to do resistive simplification from the viewpoint of the capacitor, but that would not be correct here. In fact, it'll generate an error if I try to do that. So instead, I'm going to basically have to use a test source because of the fact that I have a dependent source here, which I cannot get rid of. Now, given the structure of this circuit, I think it makes a lot more sense to use a current source here as the test source. So let's do that. And I'm going to reverse the polarity to point up. Actually, it doesn't matter which way I point it, but I'll just feel like doing it that way, so I will. And I give it an arbitrary value. Since it's just a test source, it may as well be 1 amp to make the math easy. And then again, I'm using this kind of like a multimeter. So by forcing a known current, then I can measure its voltage. So to do that, I put a SOT variable on there, and I want the positive side on the top. That's necessary so that I'll measure the correct resistance, dividing the voltage by the current. So I want to be sure that I'm kind of using the active sign convention here for the source, where the current comes out of the positive side. Okay, so I've defined that. And now the other thing I am allowed to do in this mode is to kill the independent sources, other than, of course, the test source. We don't kill that because that's what we're using to determine the resistance. But I do need to kill the other independent sources. So for example, the voltage source, that has to become a short circuit. So I'll do that. And the current source, again, the independent source, becomes an open circuit because I need to set it to 0 amps. So I'll delete that current source, and that'll simplify the circuit for me. Now remember that you don't kill dependent sources when you're killing the independent ones, because these are not inputs to the circuit. They're governed by something else in the circuit, so this does not get killed. Okay, so basically we are ready to proceed now. We can't simplify any further other than killing the sources. So we click Done. We can, however, go back into simplification mode to simplify a little bit, perhaps. So we do have 2 resistors in series there, so we might as well just combine those and make that a 5 ohm instead of the 4 + 1 ohms. So since those are in series, we'll just combine them like that. And having done that, in fact, we notice that we now have actually 2 resistors in parallel, namely the 1 ohm and the 5 ohm. Now, there is a control voltage on this resistor, but notice that that control voltage actually already appears across the 5 ohm as well, because of the way it's connected. It's connected to the same 2 nodes. Therefore, that won't be harmed by combining those 2 resistors. It'll still be there, and it'll still have the same value, even though the resistors have been combined. So we can take the product over the sum there to combine them in parallel. That's 5 times 1 is 5, divided by 6. So 5/6 would be 0.8333. And then I will remove the 5 ohm resistor so that all the resistance now is in that one element. And then we'll check that combination. And that is correct. And now notice I have something very nice. It's a single loop circuit, which is the holy grail, or one of the holy grails of circuit analysis. Now you might notice that, oh, we have a current source, and here, for example, is a resistor, and for that matter, other elements in series with it. So perhaps these other elements would be redundant. Well, normally they would be, but there's a catch here, is that redundancy doesn't apply if I care about the voltage drop across this current source, because the current going through this resistor will create a voltage drop from one side of that to the other side. So I cannot make these other elements redundant if I want to know that voltage drop. It's only if I don't care about that voltage drop that these other elements are actually redundant. So in this case, I cannot remove any of the other elements, even though they're in series with the current source, and would normally be redundant, or current splittable is another term for that. I will just compress this slightly to just make it a little neater, and that's basically all I can do now. Okay, so now I'm going to need to analyze this circuit, and because it is single loop, obviously the thing to do is to use single loop analysis. Now notice that we cannot write a KVL equation because, of course, we don't know the voltage drop across the current source. It's, as always, whatever it needs to be, and in fact that's actually what we're interested in finding. I mean, you could in principle write a KVL equation on paper using this Vs as one of the terms, but Circuit Tutor is not configured to allow that. So instead, we'll basically do the same thing by writing what we call a SOT branch voltage equation, and that's basically going to amount to the same thing. So we'll write Vs equals, so again, we need to add up the voltage drops going from the plus side here to the negative side. So the first one will be a current times the resistor, which is this one, and then we have that dependent source value here, and finally a current times the resistor again. And remember again that we cannot combine those terms in Circuit Tutor because it just doesn't allow us to do that. So we have V1 times that first resistance, which is 0.8333, and then we have a minus sign there because we're that's actually a voltage rise, the 6Vx, so we'll fill that in as 6Vx. And finally, we have another voltage drop across that resistor, I1 times the 6 ohms. And so that should be the equation for Vs, and that is indeed correct. Now we do need some more equations though. For example, we need a current constraint equation because we do have a current source in our loop. So we can write a current constraint equation, and that will simply tell us that the one current, the I1, is equal to the value of that current source. Since they're going in the same direction, notice this goes clockwise, as does the current source here, point in the same direction. So we have I1 is just equal to plus 1 amp. And then finally we need the control variable to complete the equations because that appears here. So the control variable again is Vx, so Vx equals, and once again we need something that's going to have units of volts, which would take the form of Ohm's law here. So we'll fill in the Vx, and again this is active sign convention, so we have a minus I1 times that 0.8333 ohms now, and that is correct. And basically that's all the equations we need now, so say no more equations. And now basically it just wants the answer here, and so we can just take the I1 and plug that in here, which would be simple because that's just 1, so that's negative 0.8333 for Vx, and then basically put that into here and put your 1 into here, and then just add up those things, and this is 1 also. So when we add that up on a calculator, that will give us 11.83 volts for the source voltage there. Okay, so that is correct. And now we just have to finish the R Thevenin analysis, we have to just enter the value of that resistor. And of course, that's just going to be this voltage divided by the forced current, which is the 1 amp. Because remember, this is our test source that we're using to measure the effective resistance of the rest of this circuit, including the dependent source, which we did not kill, of course. That's not allowed to be killed. So that basically is just going to be the Vs divided by 1 amp, and so that will be basically 11.83 ohms. That's why we use a nice round number here to make that easy to do the math. I mean, I could have used any value there, but it just makes sense to use 1 amp. Okay, and now basically we've determined all the parameters of the circuit, so we're ready to write our final transient expression. So we just have to select a transient voltage because that's what we're trying to find. And it's giving us the standard form for that, which again is something you probably want to learn just so you understand these problems better. So we have a particular solution here, and we have the homogeneous or natural solution here. And to fill in the blanks here, well, we think about what happens at t equals to infinity, for example, because we know that VC at t equals infinity is this value. Well, at infinity, we have e to the negative infinity, and that's going to be 1 over e to the plus infinity, or 1 over infinity, or just 0. So this term goes away, basically, at infinity, and so that value will simply be the constant value that, of course, never changes by definition in time. So we just put in the 4.833 there, and then at t equals to 0, which is the other time, or 0 plus to be precise, that we analyze the circuit, the exponential just becomes 1 because we have e to the 0 over some number. And therefore, it's just going to be the sum of these two things is equal to the 3.2 volts. So therefore, this is just going to be 3.2 minus the 4.833. And let's see if I do that on my calculator. That's going to give us negative 1.633. And then we need the time constant, which is the RC time constant for an RC circuit. So that's the resistance, 11.83 times the capacitance, which is 4 farads. So again, just do that real quick on my calculator. That gives us a rather long time constant of 47.32 seconds. And so we'll check that. And that is correct. So we're basically done with the problem now. We just say no more equations. And it does give us the option to see the complete solution. I'll just show that here for completeness. Again, it allows us to check if we missed any tricks that we could have used perhaps on the next problem. So this is the general strategy that's used. And we just have to wait while it prints a lot of stuff on the screen here. And so it starts the analysis at t equals 0 minus. And basically did what we did, changed the capacitor to an open circuit, and basically replaced the switch by a short there. And then noted the shorted resistor as we did the mesh analysis, very similar to what we did. And then at t equals infinity, once again, it's treating the capacitor as an open circuit. And it changed the switch to an open circuit, and it combined those resistors as we did, and did the mesh analysis again, so it's paralleling almost exactly what we did. And then to find R Thevenin, in this case it decided to use a voltage source, which I think probably the current source might have been easier, but you can certainly do it this way. And in that case, notice that it used a sought current to, again, simulate sort of the multimeter. In this case, it put the plus sign on the bottom. It doesn't matter where you put that, as long as you put the sought current to correspond to it. So it needs to come out of the plus side, however you hook that up. You know that when you measure, use an ohm meter in the laboratory, the red and the black leads don't matter when you're measuring resistance, because it's still going to measure a positive resistance. So it just simplified that. It combined them in parallel as we did, got the single loop circuit, and did the same type of analysis basically that we did. And so in this case, it doesn't really matter that much, I guess, whether we used a current source or voltage source. But basically, it computes the R Thevenin, gets the same value that we got using a current source, as it should, and then it just plugged it into the final expression. So that completes the problem. So thank you very much.